Industrial boilers powered factories, locomotives and steamboats, carrying the weight of a growing nation. But when one ruptured, the result was devastation on a scale few survived. Train engines shattered, riverboats vanished in white clouds of scalding steam, and entire workshops collapsed in seconds. These explosions were swift and merciless, leaving investigators to study wreckage that offered almost no answers. Why did machines trusted across every corner of American industry fail with such violent and repeating force? Before we begin, if stories like this move you, consider subscribing so we can keep preserving the lives that shaped our past. To understand why these disasters repeated for generations, we begin with the moment a moving boiler turned a routine train run into a scene of sudden devastation. The steam locomotive boiler explosion outside Chillicothe, Ohio in 1948 demonstrated how even late-era steam engines, built with stronger materials and more advanced controls, could still fail with devastating force. The train had been running a routine freight route through southern Ohio on a cold morning. The crew tended the firebox and monitored the gauges the same way they had for years. Nothing suggested that the engine carried a weakness severe enough to end the run in a matter of seconds. Witnesses along the tracks recalled seeing the locomotive approach with no signs of distress. Smoke drifted normally from the stack, and the rhythm of the drive rod sounded steady. Inside the cab, the engineer and fireman worked through familiar tasks, adjusting the draft and checking water levels. Steam engines demanded constant attention, and the men who operated them developed an instinct for small changes in heat, sound, and pressure. What they could not see was the condition of the crown sheet above the firebox. Investigators later discovered that the metal had thinned significantly. Years of heating, cooling, and vibration had worn it down to a point where it could no longer support the pressure building inside the boiler. Low water conditions contributed to the danger. When water dropped below the level needed to protect the crown sheet, the iron was exposed directly to the heat of the firebox. That exposure caused temperatures to rise rapidly, weakening the metal further. As the locomotive approached a stretch of track outside Chillicothe, pressure inside the boiler increased. The crew attempted to correct the fluctuations, but the gauges did not reveal the full extent of the danger. Water level indicators on older engines were prone to misleading readings when scale or sediment built up. Even experienced firemen could misinterpret the level during rough sections of track. These conditions created a narrow window in which the crown sheet reached its breaking point. When the failure occurred, the blast was immediate and catastrophic. The boiler ruptured upward and outward, releasing a massive wave of steam and metal fragments. The force lifted parts of the locomotive and scattered debris across the right-of-way. Residents living near the tracks reported hearing a deep, concussive roar that echoed across the valley. The engineer and fireman, positioned closest to the point of failure, suffered fatal injuries. Investigators examined the wreckage and traced the origin of the explosion to the weakened crown sheet. The report emphasized the combination of low water, overheated metal, and structural fatigue. These factors had converged in the final minutes before the blast. Although safety practices had improved by the late 1940s, steam locomotives still depended heavily on the vigilance of their crews. A momentary drop in water level or a slight misreading of a gauge could place the entire boiler at risk. The Chillicothe explosion demonstrated that steam engines, even in their final decades of service, carried the same hazards that had marked their earliest years. The power they generated relied on constant balance between fire, water, and pressure. When that balance shifted, the results were often deadly. The blast near Chillicothe became a reminder that the era of steam, despite its progress, remained vulnerable to the same hidden weaknesses that had troubled locomotive boilers for generations. The Grover Shoe Factory disaster of 1905 remains one of the most violent boiler failures in American industrial history. The boiler did not simply rupture, it launched upward with such force that it tore through the factory roof and travelled more than 200 feet before landing in a nearby field. Investigators would later say the destruction resembled the aftermath of wartime shelling rather than a workplace accident. That morning, the factory floor moved with its usual rhythm. Workers prepared machinery, belts turned along overhead shafts, and steam from the boiler house fed the building's growing appetite for power. Nothing suggested that the steel vessel beneath them had entered its final moments. The boiler had been in service for years, and its reliability had allowed a quiet confidence to build around it. Hidden inside the shell, however, Corrosion had advanced far beyond what the eye could see. Moisture collected in pockets where minerals settled against the iron. Heat created chemical reactions that slowly thinned the interior surfaces. Bit by bit, the metal weakened. This process unfolded in silence, unnoticed by the men who maintained the equipment and depended on it daily. When the boiler reached its working pressure, stress concentrated along the thinnest sections. The shell expanded just enough to widen existing flaws. Under ideal conditions, the relief valve should have limited the pressure rise, but later inspection suggested that sediment and poor maintenance kept it from responding as quickly as it should have. These factors combined to form a narrow window of vulnerability. In that window, the structure failed. The boiler released its contents in a moment of violent expansion. Superheated water transformed to steam with explosive force, driving metal outward at speeds no one inside the building could have survived. Floors collapsed immediately. The blast ignited the factory's gas lines, turning the disaster into a deadly firestorm that swept through the remaining sections of the building. The launch of the boiler itself became one of the most shocking features of the incident. The vessel cleared the factory roof and landed hundreds of feet away. Its flight illustrated the tremendous energy stored inside a pressurized steel shell. This energy was not theoretical. It was a daily presence in factories across the country, waiting to be released by the smallest structural weakness. Investigators combed the wreckage in the following weeks. Their findings showed a level of internal decay that would have been impossible to identify without thorough internal inspections. The outer surfaces of the boiler looked serviceable, yet the interior walls had lost significant thickness. Workers had noticed occasional irregularities in pressure and temperature, but these signals blended into the noise of normal operations. The Grover blast exposed a critical truth about early industrial boilers. Their failures were rarely sudden in the scientific sense. They were the final steps in long chains of unnoticed deterioration, incomplete maintenance, and assumptions that past performance guaranteed future safety. It was a pattern that repeated across the country, each time leaving investigators to study ruins that told the story only after lives had been lost. In the weeks after the Grover Shoe Factory disaster, investigators shifted their attention from the shattered boiler itself to the records that claimed to guarantee its safety. What they found inside those ledgers became one of the most troubling revelations of the entire inquiry. Inspection logs contained signatures that did not align with the dates of any known visits, and several entries appeared rushed or copied from previous years with only minor alterations. These discrepancies suggested that the checks meant to protect workers had become little more than paper routines. Boiler inspections in that era relied heavily on visual observation. Inspectors looked for scale, leaks, uneven seams, or unusual wear. Yet the Grover investigation revealed that many inspections had been carried out in minutes, not hours. Some were done while the boiler remained warm, which made internal access difficult and limited what could be examined safely. These shortcuts allowed hidden corrosion to grow unchecked. The review board discovered that one inspector had signed off on multiple facilities on the same day, despite the distances between them. This finding raised doubts about how thorough these visits could have been. The idea that someone could properly assess multiple boilers in far-apart towns within a single day contradicted the time required for genuine evaluation. It became clear that schedules and convenience often shaped the process more than safety. Workers at the factory recalled that the boiler had shown occasional pressure fluctuations. These were noted informally but never escalated into formal concerns. The culture inside many workplaces encouraged men to push through irregularities rather than report them. Lost time meant lost wages, and questioning equipment could be seen as challenging the judgment of those in charge. That unspoken pressure limited the flow of information that inspectors relied upon. One of the most revealing discoveries involved the annual inspection form for the year before the blast. The entry was written in the same handwriting as an inspection from 2 years earlier. Investigators believed it had been copied because the layout and phrasing matched so closely. This suggested that the boiler had not received the detailed assessment the factory owners believed they were paying for. These findings offered insight into why so many boiler explosions surprised entire communities. When inspections were treated as obligations rather than serious examinations, small weaknesses were never identified. A thin seam, a drooping stay bolt, or a patch of internal scale could remain hidden year after year. By the time these flaws appeared on the surface, The boiler was often already on the path toward failure. The Grover Review also highlighted the absence of standardized procedures. Different inspectors used different methods. Some brought gauges and measurement tools, while others relied strictly on sight and sound. Without uniform standards, the quality of an inspection varied widely. This inconsistency allowed dangerous conditions to pass unnoticed even when a visit was recorded on paper. The investigation's final report forced the public to confront a harsh reality. The logs that should have shielded workers from harm had provided only an illusion of safety. They reflected a process weakened by routine, haste, and the assumption that a stamped signature equaled a secure boiler. The Grover findings became a turning point because they revealed that disasters were not only born from mechanical decay, but also from human habits that favored convenience over vigilance. The Phoenix Powder Works explosion of 1915 showed how a single misplaced adjustment to a boiler's safety valve could turn routine production into a catastrophic event. Powder mills operated under constant strain, and their boilers supplied the steam that kept machinery moving. At Phoenix, the morning began like any other as workers prepared the facility for another demanding shift, unaware that pressure inside the boiler was climbing toward a point of no return. Powder manufacturing required strict timing, and the equipment drew heavy steam loads in short bursts. These sudden demands caused pressure to rise and fall more sharply than in other industries. The boiler at Phoenix had already experienced several cycles of stress before the accident. Each cycle increased the strain on its riveted seams and interior surfaces, yet the men operating the system believed the relief valve would protect them, just as it had every day before. Investigators later found that the valve, intended to open automatically at a safe threshold, had been weighted to allow higher pressure. This practice was not uncommon in facilities where managers sought more output. Adjusting the valve could push machinery harder, which sometimes improved production, but it also narrowed the margin between safe operation and disaster. At Phoenix, that margin vanished completely. As steam demand rose during the early morning activity, the boiler reached a point where internal forces exceeded what the weakened seams could hold. The added weight on the relief valve kept it from releasing pressure. With no path for escape, the force built rapidly within the shell. Workers nearby heard a deep rumble that seemed to roll through the building. Before anyone could react, the boiler ruptured. The blast tore through the powder works with devastating effect. Wooden structures splintered instantly. Machinery was hurled across the floor. The release of steam created a cloud so dense that visibility dropped to almost nothing. Those closest to the boiler did not survive the initial wave of heat and pressure. Others were struck by debris as the building collapsed around them. The destructive power of the explosion was amplified by the materials stored in the facility. Powder mills were filled with combustible dust and volatile chemicals. When the boiler burst, it disturbed this fine material, creating conditions for secondary fires. Flames spread quickly, making rescue efforts nearly impossible. For many on the property, the line between the first blast and the rising fire was only a matter of seconds. In the aftermath, investigators pieced together the sequence of events. They found evidence of corrosion inside the boiler, signs of metal fatigue along the seams, and residue that indicated long-term scale buildup. These weaknesses alone might not have caused immediate failure. It was the weighted relief valve that transformed deterioration into disaster. Without a functioning safety release, the boiler became a sealed container holding more pressure than it could withstand. The Phoenix investigation reinforced a lesson learned many times across American industry. Steam could not be negotiated with. It could only be controlled within the limits set by engineering and maintenance. When those limits were ignored, even briefly, a boiler became a source of destruction capable of leveling entire structures. The tragedy at Phoenix illustrated how a minor adjustment made for efficiency could unleash forces far beyond the intentions of the men who relied on it. The Washburn Mill explosion of 1878 is remembered for the immense power of ignited flour dust, yet the investigation also uncovered a quieter danger that had been building for years. The mill relied on an aging boiler system that had been pushed far beyond its intended capacity. Workers had trusted it because it had served them faithfully, but that long record of performance masked a slow decline that few recognized. The boilers supplied steam to a growing network of machinery that processed grain at unprecedented speed. As production increased, demands on the system rose. The boilers cycled more often, and pressure fluctuated with every shift change. Despite these strains, maintenance crews believed the equipment remained sound because it had never caused trouble. That confidence became one of the most significant risks inside the mill. Investigators found that the boilers had been installed when the facility was first modernized. Over time, they were connected to additional equipment without a full evaluation of the added load. Each new line of conveyors and grinders required more power. The boilers responded, but their internal components wore down with every surge of steam. These changes happened gradually, and the workers who heard the equipment every day grew accustomed to the evolving sounds. Steam pressure remained within what the crew considered normal, but gauges only told part of the story. Inside the boilers, riveted seams had weakened from repeated expansion and contraction. Areas near the firebox showed signs of thinning metal. Scale buildup reduced efficiency and forced hotter fires to maintain output. All these factors created conditions that could trigger failure under the right circumstances. On the night of the disaster, the boilers operated during a period of heavy demand. The mill was running late into the evening to meet production goals. Heat built steadily inside the system, and the boilers endured more cycles than usual. Workers nearby later recalled that the machinery felt unusually active, though none suspected a serious problem. The boilers had been through similar nights before, so the crew assumed they could manage this one as well. When the explosion occurred, attention focused on the flour dust that filled the air. The ignition of that dust produced the devastating fireball that destroyed the building. However, investigators noted that the initial disruption to the machinery could have been influenced by the stressed boiler system. Pressure fluctuations and mechanical strain created the conditions in which dust was stirred into a more volatile state. Although the main force of the disaster came from the dust ignition, the aging boilers played a role in the instability of the mill. The investigation emphasized how close the system had been to failure. If the dust had not ignited first, the boilers themselves might have ruptured under the load. Their condition revealed how thin the margin had become between continued operation and sudden disaster. The findings from the Washburn Review showed the danger of relying on a long service record as proof of safety. The boilers had operated without major incident for years, yet their internal condition told a different story. The assumption that past success guaranteed future performance left the mill vulnerable at the moment it needed reliability most. It was a lesson that echoed across industrial America, where aging equipment continued to run simply because it always had. The SS Sultana steamboat boiler explosion of 1865 exposed a truth that engineering reports rarely captured. Human pressure could be just as dangerous as steam pressure. The men who operated the Sultana's engines worked under conditions that rewarded speed, improvisation, and endurance, often leaving them too exhausted to recognize the warning signs that lived inside the machinery they depended on. The Sultana had been overloaded with passengers returning home after the Civil War. Every deck was crowded and the boilers were forced to supply more steam than they were designed to deliver. The engineer on duty knew the strain this created, yet he also knew that delays would anger both passengers and military officials. In that environment, pushing the machinery seemed easier than questioning its limits. Days before the disaster, the Sultana's boilers had shown clear signs of trouble. The crew noticed bulging plates near the firebox and irregular water levels during operation. These issues pointed toward thinning metal and uneven heating. Proper repairs would have required shutting the vessel down for an extended period. Instead, workers were instructed to apply a patch, a quick fix that tightened the leaking area but did not address the underlying weakness. Such temporary repairs were common on riverboats under pressure to stay in motion. Crews were often stretched thin and expected to keep engines running through weather, crowds, and tight schedules. The men responsible for the boilers laboured long hours in the heat of the firebox. Their eyesight blurred from smoke and steam. Fatigue became part of the job, and with fatigue came a narrowing of attention. On the night of the explosion, the Sultana was travelling upriver against a strong current. The boilers worked harder than usual, and the crew fought to maintain pressure while keeping water levels stable. Low water near heated surfaces created the most dangerous conditions a boiler could face. When metal overheated, even a small drop in pressure could trigger sudden expansion and catastrophic failure. Shortly after midnight, the crew heard a sound that they described as a deep roar. The first boiler failed, and the force of the rupture triggered the others in a chain reaction. Superheated steam and fragments of iron tore through the decks above. The blast was so powerful that survivors recalled seeing a bright column of steam rise into the night sky before darkness closed around them again. The human cost was enormous. Many passengers were thrown into the river, while others were trapped in the shattered remains of the vessel. The crew, positioned closest to the boilers, suffered the greatest losses. Their long hours and constant exposure had placed them in the centre of the disaster. The investigation that followed revealed the full extent of the vulnerability. The patch applied earlier had concealed the weakened plate but had not restored its strength. The boiler had operated through the final hours of the journey on the edge of failure. The crew never intended to place anyone at risk. They simply worked within a system that rewarded persistence over caution and speed over safety. The Sultana tragedy demonstrated how human factors shaped the fate of many boilers across American industry. Exhaustion limited judgment. Pressure encouraged shortcuts. When those conditions combined with aging metal and fluctuating loads, disaster became almost inevitable. The lessons learned on the Mississippi River echoed across factories and rail yards for decades to come. The Dixon Boiler Works explosion of 1924 revealed how a repair intended to solve a problem could instead create the conditions for disaster. In the months leading up to the event, workers had noticed a persistent leak near one of the boiler's seams. The leak suggested that internal pressure was finding a path through weakened metal, yet production demands kept the facility operating with little downtime. When the decision was made to repair the boiler, the work was completed quickly so operations could continue with minimal interruption. Investigators later learned that the repair involved installing a patch plate over the weakened area. This method closed the visible leak, but it did not restore the original integrity of the structure. The uneven distribution of stress around the patch created new points of strain. Heat cycled through the area each day, expanding and contracting the metal while the plate restricted natural movement. Microcracks began to form in places no one could see. The workers who completed the repair followed common practices of the time. Speed mattered because shutting down a boiler meant shutting down the machines it powered. Every hour offline represented lost wages and lost output. Under these pressures, repairs often aimed for immediate function rather than long-term strength. Few understood how even small misalignments could become critical as heat and pressure intensified. Over the following weeks, the patched boiler returned to regular service. Its exterior gave no indication of the changes occurring beneath the surface. Pressure cycles widened the microcracks around the patch, allowing water to reach overheated metal. The presence of moisture in these vulnerable areas created a chemical environment that accelerated corrosion. Each day, the boiler moved closer to the threshold at which a full failure could occur. On the morning of the explosion, workers recalled hearing a faint tapping sound from inside the boiler house. The noise resembled metal shifting under heat, a sound that had become familiar in their work. Within minutes, the pressure gauge rose sharply. The crew attempted to stabilize the system, but the weakened seam had already reached its limit. The boiler ruptured with a force that shattered windows across the street and sent debris through the walls of nearby buildings. The aftermath revealed the hazardous combination of stress, corrosion, and structural imbalance created by the patch. The explosion originated exactly where the repair had been installed. Investigators found remnants of metal that showed clear signs of fatigue. Their analysis concluded that the patch had redirected pressure into surrounding areas, making the boiler more vulnerable than before the repair. The Dixon event illustrated a hidden danger in many industrial settings. Repairs performed under pressure often addressed the symptom rather than the cause. The tools and techniques available at the time could not always ensure that the repaired area matched the strength of the original shell. Workers and managers placed trust in fixes that appeared solid from the outside, unaware that internal stresses were building with each cycle of heat. The tragedy also emphasized the need for stricter oversight when returning boilers to service. At Dixon, there was no extended inspection following the repair. The boiler resumed operation almost immediately, leaving no opportunity to test its stability under controlled conditions. This decision reflected a broader mindset across American industry, where efficiency overshadowed caution and where temporary fixes were often treated as permanent solutions. The Dixon explosion became a reminder that a boiler was only as strong as its weakest point. A rushed repair, even one made with skill and good intention, could become the starting point for a chain of events that ended in devastation. The lessons drawn from the wreckage underscored how fragile safety became when repairs were guided by urgency rather than engineering. The Allegheny Arsenal boiler explosion of 1862 unfolded inside a facility that had grown far beyond the capacity of its original steam system. In the early years of the arsenal, the boilers had powered a modest collection of workshops. By the time of the disaster, the site had expanded into one of the busiest munitions centres in the country, with new buildings, heavier machinery, and a constant surge of wartime production. The boilers, however, remained fundamentally unchanged. The expansion placed demands on the steam system that few had anticipated. Each new workshop added pipes, valves, and heating requirements. The boilers cycled more frequently as workers operated machinery around the clock. Pressure fluctuations increased as the arsenal struggled to keep pace with military orders. Despite these rising stresses, the equipment was considered reliable simply because it had performed well in the past. Investigators later found that the arsenal had not conducted a full evaluation of its steam needs after expanding. The original boilers were connected to additional lines without a complete understanding of how much load they could sustain. This oversight meant that the system operated near its limits long before anyone realized it. The machinery drew steam faster than the boilers could replenish it, creating sudden drops and spikes that weakened internal components. On the morning of the explosion, workers reported that the boiler house felt unusually active. Steam lines vibrated more than usual. The firemen fed the furnaces continuously to maintain pressure. They believed the system was working as intended, yet the boilers were enduring forces far greater than those for which they had been designed. Riveted seams strained under the rapid changes, and internal surfaces wore down at an accelerated rate. When the failure occurred, the blast struck with devastating force. The boiler ruptured near one of its most overstressed seams, releasing steam and metal into the surrounding structures. The explosion echoed across the arsenal grounds, and the shockwave damaged nearby buildings. Workers caught in the blast zone suffered injuries from scalding vapour and flying debris. The scene bore the marks of a system that had been pushed past the point of endurance. In the aftermath, investigators noted that the arsenal's growth had outpaced its safety infrastructure. The boilers had been adequate for the earlier facility, but they were no longer suited to the expanded operation. The absence of updated assessments meant that no one had recognized the danger created by the increased demand. The explosion illustrated the consequences of relying on equipment that had not evolved alongside the industry it served. One of the most significant findings related to maintenance. As production increased, the time available for detailed inspections decreased. Crews performed quick checks and cleared soot, but they rarely had the opportunity to examine internal surfaces carefully. Scale build-up reduced efficiency, forcing hotter fires and higher pressures. These conditions eroded the margins that once protected the system from catastrophic failure. The Allegheny event revealed a pattern that would repeat across American industry. Factories grew larger, machinery became more powerful, and demand intensified, yet many steam systems remained anchored in earlier decades. The belief that a boiler could continue to perform, simply because it always had left facilities vulnerable. At the arsenal, that belief contributed to a disaster that highlighted the gap between outdated equipment and modern expectations. The tragedy demonstrated that expansion without evaluation carried significant risks. A steam system designed for a smaller operation could not sustain the forces of a much larger one. The Allegheny explosion became a lesson in how industrial growth, when unsupported by updated engineering, could turn trusted machinery into a source of sudden destruction. The Lynn gas and electric boiler explosion of 1909 showed how dangerous it had become for a company to rely on older equipment when safer technology was already available. By the early 20th century, water-level gauges, fusible plugs, and improved safety valves were beginning to reshape boiler operation across the country. Yet at Lynn, some of these innovations had been slow to arrive. Cost, habit, and confidence in the old system delayed upgrades that might have prevented the disaster. The boilers at the plant had been in service for many years. Their design reflected a period when steam production grew faster than safety standards. Although new devices existed to warn operators of low water and overheating, the equipment at Lynn still depended on earlier methods that required constant observation. The responsibility placed on the crew was heavy, and the margin for error was thin. On the day of the explosion, the boilers were supplying steam for electrical generation during a period of high demand. Operators monitored their gauges as they always had, watching water levels and pressure ranges with practiced familiarity. Nothing in the readings suggested that the system was nearing a critical point. However, the indicators they relied on were not as responsive or accurate as the modern devices that had begun appearing in newer facilities. Investigators later found that one of the boilers had suffered from a dangerously low water condition. With less water covering the heated surfaces, the metal grew increasingly hot. The crew did not receive immediate warning because the older gauge glass did not reflect the true water level. Newer designs offered improved visibility and reliability, but Lynn had not yet adopted them. This oversight created the conditions in which the boiler could overheat without clear signs. When the failure occurred, the rupture tore through the boiler house and sent fragments of iron into surrounding structures. The release of steam created a shock wave that reached workers across the property. The force of the blast indicated how hot the metal must have become before the final moment. That temperature rise, hidden from the crew, had transformed the boiler into a vessel primed for catastrophic failure. In the aftermath, investigators examined the safety devices attached to the boiler. They found that the older relief valve functioned, but its response had not been fast enough to counter the rapid temperature change. A modern system with more sensitive controls might have released pressure earlier. The absence of updated equipment played a central role in the sequence that led to the explosion. The inquiry also revealed that decision-making at the plant emphasized maintaining production levels. Upgrades required shutting down portions of the system, which could interrupt service and reduce output. Managers believed the existing boilers were reliable and saw little reason to replace components that had worked for decades. This confidence ignored how aging equipment responded differently to the demands of modern industry. The Lynn event illustrated the hazards that emerged when technology advanced faster than adoption rates. New safety measures could not protect a facility that chose not to install them. The disaster became an example of how outdated equipment, even when well maintained, could not match the capabilities of newer systems designed to detect early signs of trouble. In the end, the explosion underscored a broader truth about industrial America. Progress in safety only mattered when it reached the places that needed it most. At Lynn, the gap between available technology and existing practice created a moment in which a trusted boiler failed without giving the crew the information they needed to prevent it. The lessons drawn from the ruins became part of the growing movement toward mandatory safety standards, which aimed to close that gap for good. The aftermath of the Grover Shoe Factory disaster set in motion one of the most important safety transformations in American industrial history. The devastation had been so complete that investigators struggled to identify where the boiler had first failed. Fragments were scattered across fields, and the building itself had been reduced to ruin. Communities across the country realized that if such destruction could strike a respected factory, then similar dangers lived inside every boiler that powered American life. Public reaction to the blast carried unusual weight. Local newspapers documented the wreckage in stark detail. Families demanded answers, and business owners feared similar events could happen in their own mills. For the first time, the voices calling for change were not limited to engineers. They came from workers, citizens, and inspectors who understood the scale of the threat. Pressure built for a system that could prevent another tragedy. In the years that followed, insurance companies and mechanical engineers began cooperating more closely than ever before. One of the central groups in this effort was the Hartford Steam Boiler Inspection and Insurance Company. Its inspectors had long argued that inconsistent examinations created unnecessary risks. The Grover blast strengthened their position and provided a clear example of how overlooked corrosion and inaccurate records could lead to catastrophic results. These efforts led to the development of a formal set of rules that would become the foundation for the Hartford Boiler Inspection Code. The code established minimum safety standards for design, operation, and maintenance. It required regular internal inspections, accurate measurement of metal thickness, and the installation of reliable safety devices. For industries accustomed to setting their own practices, the new regulations represented a significant shift. Implementing the code was not simple. Many factories resisted because compliance required time, training, and occasional shutdowns. Older boilers often needed modifications or replacement. Managers argued that their equipment had run safely for years. Yet officials pointed to the ruins of the Grover site as proof that assumptions about safety could not be trusted. The new guidelines aimed to remove guesswork from boiler operation. Inspectors trained under the Hartford system brought a new level of consistency to the field. They used standardized procedures to evaluate boilers and kept detailed records that allowed long-term tracking of wear and deterioration. For the first time, factories began to understand how quickly internal surfaces could change. Problems that once went unnoticed now appeared in clear, documented patterns. The code also encouraged the adoption of improved valves, gauges, and fusible plugs. These devices offered early warnings of dangerous conditions and provided operators with more accurate information. Although factories initially resisted the expense, the cost of compliance was far lower than the cost of rebuilding after a major explosion. The memory of the Grover tragedy helped shift public opinion toward acceptance of the reforms. By the early 20th century, the Hartford Code had influenced legislation across several states. Its principles shaped national standards that extended far beyond the industries involved in the original reform effort. The legacy of the Grover blast became one of prevention rather than destruction. Each facility that adopted the new rules reduced the likelihood of repeating the same chain of events. The movement that began with a single disaster ultimately protected thousands of workers. It replaced informal habits with structured oversight and transformed boiler safety into a disciplined field grounded in engineering rather than convenience. The reforms showed how tragedy could lead to progress when communities refused to accept preventable loss as an unavoidable part of industrial life.